So far, both lectures last week I have successfully recorded. Didn't have any technical issues. Okay, so I will post. Okay, let me share my screen. Let's continue. Last time we talked about the steady state, unsteady, uniform or non-uniform flow. Okay, let me share my screen. Okay. Still remember what is the uniform flow, non-uniform flow, unsteady, steady state flow? Do you remember the example I gave in a indoor environment, like in a room? Okay, your AC is on. Okay, inside this room, first my question is this flow inside your room uniform or non-uniform? Anybody?
Non-uniform.
Why is non-uniform? Well, as an engineer, as a good habit, talking, when you talk about technical stuff, don't answer the question until you know how to explain it. Why is it? Okay. Don't trust your intuition sometimes. Yes or no question is kind of like a multiple choice question, something like that. Don't answer.
Because it changes with time.
No. My question is the flow uniform or non-uniform? I think who answered it previously? The girl? I didn't see the name.
I did.
Oh, okay. So could you answer the question why you think it's uniform flow? Oh, I'm sorry. You said non-uniform, right?
You said non-uniform.
Yeah. Why it's non-uniform flow?
Because it's a function of velocity.
Because what? I'm sorry.
It changes from a function of velocity.
Changes in the function of velocity. You answered half correctly. What do you mean by change in the function of velocity?
Like
change in terms of what?
Time.
In terms of time, then it's nothing to do with uniform or non-uniform. Just like the other guy who answered, you say it's unsteady. I said, no, it's my question is it uniform or non-uniform? I didn't ask you steady or unsteady.
Yeah, that was me. Sorry about that. I answered the unsteady.
Okay.
Would your last question, would the answer be position?
That's right. Okay, it changed. It changes in terms of position. Okay, let me repeat the example I gave last time. I said in this room, I give you 1,000 sensors, velocity sensors. Okay, it's not possible, but let's say assume infinitely small velocity sensors. You evenly placed it inside this room. Okay, evenly placed inside this room. So if you want to say it's uniform or non-uniform flow, look at the reading from this 1,000 sensors. Okay. If the reading from this 1,000 sensors on 1,000 different locations, they are all the same. Okay. That means it's uniform flow. Okay, does that make sense? Okay, this is very okay. This is very confusing. Later on,
also with the AC temperature you said.
Yeah, I'm not talking about the temperature. I'm talking about the flow, but it's okay. The velocity-wise, okay, you're talking about flow means velocity, right? I assume that sensor can tell you not only the magnitude, but also the direction of the velocity, okay? Remember, velocity is a vector, okay? So if on all 1,000 sensors, it give you the exactly same velocity reading, exactly same velocity direction. Okay, it's not only the value, okay, but also the direction. Velocity is a vector. Do you by chance know that velocity is a vector? Anybody?
Yes.
Okay, so good. So if the magnitude and the direction are all 1,000 sensors, which are evenly distributed inside the room, they are all the same. That means it's a uniform flow. Is that clear to everybody? So uniform or non-uniform in terms of space, okay? Does the velocity change with space at any given instance? Okay, you look at the snapshot of an instance, screenshot, for example, a snapshot of an instance for the entire room, okay? It's a freeze the moment, like let's say in this moment, okay? Does the velocity everywhere the same? Okay, that's a question. Basically, you want to ask yourself before you answer this question, uniform or non-uniform. Okay. Could you guys turn on the video? I mentioned many times, right, in the last week in the class. Please, everybody turn on the video so I can, see your face and probably I try to communicate with the question I ask. I want to have some answer, see if you understand. Okay. Make sure you turn on your video if you can. Does that make sense? Is my explanation? Okay, so it doesn't matter the time. Okay, don't worry about time. Uniform and non-uniform is nothing to do with time. It's at any given instance. Okay, on this instance, it could be uniform. Next instance, it could be uniform, but that may change from instance to instance. Okay, so uniform flow, it has to be on any instance. Okay, on any given instant in the space, the velocity doesn't change. Okay, the same. Okay, now come back to unsteady or steady. Is that same flow in the room, AC flow, is it steady state or unsteady? So exclusively, if you talk about unsteady and steady, you never think about space. Okay, it's only exclusively you talk about time.
Yeah.
Okay, so basically it says, okay, at any given space location, okay, the sensor 155, the sensor number 155, let's say, okay, is the sensor give you reading at different times, give you different readings at different time? If your answer is yes, then it's an unsteady flow. I don't care about any other location. If one location, okay, one location, the velocity changes with time. Okay, at least at that location, it's unsteady flow. Okay, so if you only talk about time, hey, unsteady. But so is the air conditioning flow is steady or unsteady? See, the question is not complete. I don't know if the air conditioning is running all the time or not. It runs, it stops, it runs, Then if that's the situation, it stopped, then the velocity changed. Okay. When you stop, the velocity gradually die down and it becomes zero. Okay. Think about that sensor is always there. You have 1,000 sensors. Yeah. Each given sensor give you readings any given time. Okay. If it changes with time, that means it's unsteady flow. Okay. So think about the space. You study fluid mechanics, again, I think in the first class I mentioned, you are not really looking at individual air particles. Okay, that's the fundamental difference between fluid mechanics and the solid mechanics. Okay, solid mechanics, you look at the ball, look at the pendulum, look at the object. Here, the fluid object is the air particle, but you're never look at the air particle. You're never interested in the air particle. You're interested in the space that the air particle goes through. Does the space get affected by the air particle? Okay, so that's a different way in looking at the problem. So, okay, in the space, in the particular location, for example, where you sit, you experience airflows, okay? Then 9 o'clock air turn on, then you have velocity on yourself, okay? Then 10 o'clock it turned off, you have no velocity. So in your position, it is unsteady, okay? If it's unsteady, then well, if the air keep coming in the same, never stopped, it might be look like a relatively steady state, right? Okay. Is there any questions? Please let me know. Please jump in if you have any questions. Okay.
So you said, just to clarify, you said unsteady flow, you don't care about the space, just the time, because it's at a different time. And then for the steady flow, the same thing is at the same time.
Yeah. I think what you think is what you understand is right. Okay. You're in the mathematical form. Okay. You have a really good question here. In the mathematical form for the velocity field. Now you're not looking at a individual air particle. You're looking at the space, the entire space. Okay, your room. So the velocity is a function of x, y, and the z. Right? We're in the 3D world, right? Is that right? You understand function, right? You already passed the
Yes,
Cal 1, Cal 2, Cal 3, right? So velocity changes on every different location, x, y, z, every coordinates in the room. Okay, it's a function of x, y, z, as well as a function of t. Okay, so kind of 4 dimensions here, right? 3 dimension in space, 1 dimension in time. Okay, so what does steady state means? Steady state means the velocity is a function of x, y, z only. It's not a function of time. Of course, velocity still change with space, but it doesn't change with time. Okay,
All right.
so that means it's a steady state.
All right. Thank you.
You're welcome. This is unsteady. So what about the uniform velocity? So velocity is a function of t only, or not a function of x, y, z at least. That's a uniform.
Dr. Zhang,
Yeah.
what does the C represent when it says velocity is equal to C or volume is equal to C?
Constant.
Constant. Okay.
Velocity equals to a constant. C always referred to as constant. Okay. Okay. Because later on we're going to see problem like you're going to terribly confused if you're not clear right now for the velocity, for the uniform, non-uniform. Because in the pipe flow, sometimes we use uniform velocity to represent in the pipe flow, but people will confuse what do you mean by uniform. It still changes from one pipe to the other pipe. Okay. Doesn't matter. That's if it's unsteady, yeah, it changes with time, of course. But it's still, look at the one cross section. It's uniform velocity. Okay, theoretically it's not uniform. Okay, but we assume it's uniform. At that time, people will be very confused. But I just want to make sure everybody understand here. Okay, just use the example in your mind. Always has the example. Okay, can you have an example of uniform flow in your mind? Think about any uniform flow. What does it look like? Think about you doing a wind tunnel experiment. Wind tunnel. Okay, wind tunnel. Did you see the wind tunnel? We have a wind tunnel. It's not working now. Okay, ETL 121. Okay, and okay, when they turn on the wind tunnel, there's the filters, Honeywell, anything in the front to regulate the flow. So when the flow going to the test session, it's a uniform flow. Okay, so in the test session, you see the velocity is the same, straight, everywhere. Okay, but this is uniform, but it could be unsteady because the velocity can change with time. You can adjust the velocity values. You can adjust, hey, it's 100 meters per second. It's 50 meters per second, 72 meters per second. You can adjust it, right? During the adjustment, the velocity changes. But no matter how it changes the value, but when you look at that space, wind tunnel space, the test section, the velocity is always the same everywhere. It changes 72 meters per second, then everywhere 72 meters per second. Okay, if it becomes 50 meters per second, then everywhere is 50 meters per second. Okay, so that wind tunnel example is a unsteady state uniform flow. Of course, there's no absolute uniform. Always, you know, it's not absolute, right? But yeah, relative uniform, we can consider it's uniform. So it's an unsteady state uniform flow in the test session of a wind tunnel. Does that make sense? Try to use examples to understand the concepts. Okay, is that good? Is that a good example, like wind tunnel? Okay, then this is empty wind tunnel, what I'm talking about. Now you put a small car in there. Okay, then the flow in the wind tunnel is still uniform or not? Now you have an object in the wind tunnel test session. Okay, do you know wind tunnel test? You see those videos, right? You can put those airplanes in there, right? So you can put even a race car in there and then test it. They blow smoke to it, right? Okay, so is the flow uniform when you place a object in the wind tunnel?
No,
Right? No, it's not uniform because the velocity changes. Of course it changes. Behind the car.
unless it was like perfectly aerodynamic or something.
No, even if it's perfect aerodynamic, it changes because your velocity is always smaller behind the car. Do you agree?
Okay.
In the space, okay. You have to change the idea. I mentioned it many times. I emphasize it here. When you look at fluid mechanics, you're looking at the space. Everything we said here, steady state, unsteady, uniform, non-uniform, whatever we said, is according to that space. We're talking about that space. Okay, we're not talking about that car, the race car you put in the wind tunnel. No, nothing to do with. We're talking about the space around the race car. Okay, is all the velocity, every velocity, all the velocity in the space around the race car uniform, the same?
No.
Absolutely not, right? I can draw it with you, right? I think that I want to spend a little bit more time on those concepts now. Okay, you blow air to it. I use the arrow representing air. Everybody understand? Okay, let's take do the benchmark, right? Without anything in there. Okay, this is comparison. This is with race car, without race car in the wind tunnel. Without the race car, the flow is just straight, right? Do you agree? Everywhere is straight, right?
Yes, sir.
Yeah. This is a uniform flow. Okay, you have to look at the space, the entire this space you're interested. Okay, in that space, velocity doesn't change, it's uniform. Okay, how about this race car situation? Oh, your velocity is in the beginning, before hitting the car is straight. But what about the velocity after hitting the car? It turns, become vortex, right? In the top, away from the car is still the same, but behind the car, the velocity being blocked. It's not straight anymore. It's blocked by the car. You're not going to penetrate the car. You're going around it. Is that right? Is the velocity any more straight? It's no longer straight anymore. Just not like the bottom situation. In the bottom situation, velocity everywhere in the space is just a value in the straight.
So would the bottom one also be considered steady?
It's steady or not, I don't know, basically. Depend on do you change the velocity or not. But when you change it, you change the switch, if there's a switch, it's controlled by computer, right? You say you change the velocity, but the velocity change all at the same time. At any given instance, you still see it's still uniform, but it changes with time, then it's unsteady. Okay, I set 100 meters per second, never change, then it's a steady state uniform flow. But depend on you, do you change it? If I keep changing it, okay, if my velocity is this, sinusoidal, it's possible, right? This is the velocity value. Let's say maximum 100, 0, negative 100. Okay, this is x-axis is time. Okay, so at any given time, 8 o'clock here, you have a velocity value. 9 o'clock, you have a different velocity value. But if you look at the space, it changes altogether. If it becomes 70 meters per second, everywhere is 70 meters per second. Okay, this is the space of interest. Okay, in the space, do you see that reality? If you operate this wind tunnel, you can change the speed, right? Is that right? Do you agree? Okay, when you change the speed, then of course the thing becomes unsteady. Okay, is that right? It changes with time. Okay, unsteady, but it's still uniform. When you look at it at different time, the speed changes. Hey, speed changes, but it's still straight flow, just with a little bit less magnitude. But everywhere,
So the bottom graph is unsteady and uniform?
That's right. Do you agree? Unsteady and uniform. Still depend on you change it or not. If you don't change it, there's no operator.
And just so I'm clear about what that would represent, would that mean that it's like going one way and then come back the other way? How do you get negative 100? So it's blowing one direction and then turns back the other direction?
Velocity is a vector. The sign representing the direction.
Yeah, I'm just making sure I'm reading that.
Yeah.
Right.
Negative 100 means the opposite direction. Let's go from right to left. Okay. So if you can make that happen, you can. The fan, you can actually, the wind is driven by the fan, right? The rotating fan. You can change the direction of the rotation. Then become a suction. Okay. In wind tunnel, you can change the direction of the flow too. Okay. So this is just an example. You don't have to understand how it operates like this, but that's just an example. It shows you that the velocity of the wind tunnel changes with time. Okay, but when you look at the wind tunnel any given time, the velocity is uniform there. Okay, it's uniform in there, but it changes with time, so it's unsteady. Is that clear to everybody? Everybody, I mean everybody. I literally mean everybody. Okay, since you made the effort to attend the class, I want you to learn everything in the class. Don't want you to spend much time out of the class. Okay, be more efficient. Okay, if you have a question, just jump in and ask. Okay, now we go to the top example. Now this flow is non-uniform because inside this space at any given moment, you look at it, the velocity is not the same everywhere. Okay, you agree? They're not the same everywhere. Behind the car has a little velocity. Okay, on top of the car, velocity is higher. Okay. Good, steady. So is it possible for any combination? Is it possible non-uniform steady? Is it possible uniform unsteady? Uniform unsteady, I already said this is a uniform unsteady, okay? But is that possible for non-uniform steady?
Yes.
Yeah, it's possible. It's possible. For example, in this test one. Okay, let's don't worry about turbulence. Assume there's no turbulence. Okay, it's just flow is regular like this. Okay, so if you keep the fan on forever, it's always has a certain coming speed. Okay, so this entire space, it looks the same anytime you go visit it. Okay, it's non-uniform, right? Do you agree? First of all, do you 100% agree this is non-uniform? Okay, if it's non-uniform, oh good, non-uniform, then but at different times when you look at it, it's the same distribution. That means it's a steady. Huh? What do you say?
But I said it's the same flow, but not at the same time. That's what you're saying.
Yeah, it's the same flow. It's the same. You take a snapshot of you have phone, take a picture, the flow like this. For example, if you can see the flow, okay, they put smoke in there, you can see the flow. Okay, take a picture, 8 o'clock, it's look like this, okay?
So your sensors all have different velocity, but the velocity on each sensor doesn't change?
That's right, then become steady state. Okay, think about that. That's why they created this uniform, non-uniform, steady and unsteady. That's in terms of two different aspects. Okay, so this example test one I show you, it could be non-steady, unsteady. I'm sorry, it could be steady and non-uniform. Uniform or non-uniform in terms of space. Okay, steady and unsteady is in terms of time. Okay. I'm telling you, most of the flow you see, 90%, 95%, most of the flow you see is unsteady, non-uniform. That's the most general case. Okay, unsteady, it changes with time, it changes with space. Okay, it changes with space and it changes with time. Okay, I would like you to have an example of this kind of each combination in your mind. Okay, what's the example of that, you know? So yeah, that would be great for you to understand. Okay, any questions on this topic before I move on? Good. Okay, it's very important. Later on, please remember this class today. Okay, later on when we talk about, we don't have much time to spend, and when we go into the pipe flow, we say it's uniform, then you forget what does that mean. Okay, so please remember this, very important. Okay, the other classification usually we talk about in the class, it is laminar and turbulent. Laminar flow and turbulent flow. Okay. I don't want to reach too much detail of this. It's a very complicated concept on the turbulent flow part. But laminar flow, it doesn't mean it's uniform flow. It can be, okay, let's say flow over a cylinder. Look like this, okay, flow of a cylinder. The flow is very regular with a very sticky, you know, flow. It's very heavy flow. It's not very light like air, maybe oil or more heavy fluid, okay? And then the flow become very regular and it doesn't change with time. Okay, sometimes it still do change with time, but it's still easy to characterize. Okay, we have governing equation to solve. Basically, Newton's second law. Based on that, the governing equation with all the flow we can solve is laminar flow. It's very regulated. Okay, predictable. Okay, And the flow is basically slow. That's called laminar flow. This is still, it's not, of course, those straight flow is all, of course, laminar. Okay, very straight, very regulated. That's the simplest example. But I want to raise this example of a flow over a cylinder. It could be laminar too. Okay, if the flow is relatively heavy and sticky. But what is the turbulent flow? Turbulent flow is in the, we can say this example, when you use the same cylinder, okay, but you increase the speed very fast, okay, very fast, then, and the fluid is light, okay, less sticky, then it's hard to hold the regularity like this, okay, it becomes very chaotic and unpredictable. Then the vortex start to shed everywhere. Okay. Of course, in the wake is still, in the far away is still kind of like straight, but in the wake of the cylinder, it could be very turbulent, but a lot of small eddies, very unsteady. Again, I use the word unsteady. It keeps changing with time. Any instance, and we take a picture, it looks very different, unpredictable. And all the conservation law, equations, Newton's second law, all breaks down. Again, the turbulent part. Okay, so this is the laminar, and this is turbulent. Turbulent has the characteristic of unpredictable and chaotic. Okay, you take a commercial flight, often the pilot will say, hey, there's a turbulence down there, it's bumpy, right? Why the airplane suddenly become bumpy and vibrate? Because the airflow, the airplane experience very strong vortices, eddies around it. Okay, it creates a pressure variation. So
the examples you have on the screen are ones that would be in a pipe or not exposed to atmosphere.
it's not the pipe flow. This is the flow outside a cylinder. Okay, sometimes
I see. Okay.
Okay, it's not inside the pipe. Okay, good question. A lot of people confuse. If you see a circle, they think about it's a pipe. No.
Yeah, because isn't it like if you turn your water faucet on, as soon as it starts sucking in bubbles, that's when it becomes turbulent?
Yeah. You see the bubble, and basically it's an indication of turbulence. Okay. The condition is usually for the turbulent flow is fast. Okay. If the flow is fast, just like an airplane flying in the sky, in the air, in the atmosphere, so it's kind of like fast. Okay, if fast, you create turbulence. Okay, and if it's slow, I'll give you an example, like a molten lava. Did you see the, probably if you went to Hawaii, the big island, they have a molten lava always. They're running down. Sometimes you're lucky you can see it, right? But molten lava, it's a flow, very, very heavy. It's slow, slowly move down. Okay, think about this. This is the example of laminar flow. Okay, the motion and the distribution of the lava flow, it can be calculated. Okay, it's very predictable. Okay, then in comparison, it's like the airflow around a flying airplane. Okay, it's very turbulent, very unpredictable. Okay, does that make sense? So to differentiate the laminar flow and turbulent flow. I'm talking about when you look at it, how does it look different between laminar and turbulent, right? But in reality, flow, you can see it. Right? You can see some of the flow. You cannot see all the flow. For the airflow, nothing you can see. If you cannot see it, for example, the airflow around the airplane, can you see it? You cannot see anything. If you can't see it, how do you decide it's laminar or turbulent? Okay, so in this fluid mechanics topics, eventually everything rely on the mass. Okay, you use some equation to decide it's laminar or turbulent. So for Reynolds number is a number we use to determine its laminar flow or turbulent flow. Okay, later we're gonna introduce what is the equation for the Reynolds number. Basically, if the Reynolds number is small, then that flow is laminar, and the Reynolds number is big, then it's turbulent. Okay, then it's easy. You don't have to see it. You just need to calculate it. Okay, based on the velocity, dimension, and the viscosity. Okay, we'll talk about it later. Okay, just this is the introduction. Okay.
Just to clear up what you said earlier and make sure I heard you right, you said laminar flow doesn't necessarily mean that it's uniform, but it does mean that it's steady.
It's not necessarily steady. Steady flow is kind of how to say, it's a sufficient condition, not necessary condition. Steady flow, I think most of the time it is laminar.
Okay, so
but the laminar flow doesn't have to be steady state. If it's unsteady, it still can be laminar flow.
Okay, so none of them fit. None of them are always steady or uniform or ununiform, right?
No. I think for the laminar and the turbulent, laminar could be any of the combination previously you see. Uniform, unsteady, non-uniform, steady. It's all possible. Okay, as long as it's slow and it's regulated and regular, you know, seems like it's predictable and slow, and you know, you see the structure clearly, and the structure, flow structure, although sometimes it's unsteady, but it's repeatable. Okay, and the turbulent is very chaotic, unrepeatable. Okay, you see one moment to look like this, it never happened again, maybe. Okay, you see my point? Unpredictable and chaotic, that will be turbulent. And the laminar, it could be unsteady, it could change with time, but the pattern is repeatable. The changing, you know, periodic, is repeatable. Okay, so yeah, the thing is, you know, this is the first class you had fluid mechanics. You know, sometimes you experience more, and later of the semester, probably you will be more familiar with what I'm talking about here. Okay, I think in conclude this, and you have to look at the problem really differently. Now you don't have an object; you're looking at the entire space. Everything is due to the change of that inside that space. Okay, a space. Then if everything changes, then the turbulence, then it will be all the classification is based on, you know, whatever you observe in that space. Okay. Okay, laminar turbulent is another thing we will you know, talk a lot about later in the semester. And those equations for laminar flow and turbulent flow are very different. Okay, we have analytical solutions for the laminar flow problems, but we don't have analytical solutions for the turbulent flow problems. For the turbulent flow problem, we only have empirical solution or measurement. Okay, correlation from measurements. Okay, keep in mind. Anything we talk about theoretical analytical solution, it's only for laminar flow. Okay, so in that sense, see, when you see actually try to solve a problem in the future, you will ask yourself, is the flow laminar or turbulent? I have two sets of weapons, equations. Okay, if it's laminar, then you have actual analytical solutions. In the real time in your career, if you see, hey, the flow is turbulent, I don't have an analytical solution. Probably I'm going to do some measurement, or maybe I'm looking for previous measurement results. Okay, to do some calculation. Okay, I guess anything else? Oh, yeah, state of matter. Maybe we want to talk a little bit about the state of matter. States of matters. Okay, because this is the fluid mechanics, right? So we are looking at a couple states. Okay, we'll study. If it's a solid, we're not studying it, right? This is out of the scope of our class. So how many states of matters on Earth or in the universe?
4.
4? You say, what are the fours?
Solid, liquid, gas,
solid,
and plasma.
liquid, gas, and plasma.
Solid, liquid, gas, plasma. Which side? Solid side or gas side?
Gas side.
Yeah, plasma. Okay, so it's like a heat, right? If you're receiving heat, a lot of matter is gonna go from solid to liquid to gas to plasma. Is that right? Okay, solid, liquid, gas is pretty straightforward. What is plasma, by the way? Can you explain to the class? What's the difference between plasma and a gas? What does the plasma look like? Does it look like gas or look like a solid?
Not 100% sure.
But I'm pretty sure plasma doesn't look like a solid, right? I think
No, I know the sun generates plasma. Like some of the rays and things we see are actually plasma.
Yeah, exactly. You're right. I think I read an online article a while ago talk about the 99% or 95%, I forgot the exact number, of the matter in universe is plasma. You see, most of the matter of the sun, for example, is plasma. Probably 99% of the matter in universe is plasma. Okay, plasma is look like a gas. Okay, but it's conductive. Okay, gas is not conductive, right? Like air, you know, the air surrounds you, it's not conductive, right? Electrical conduct, it's not, right? Otherwise, everybody die already, electrified, because you have plug in your room.
Could lightning be a form of plasma? Or like a welding or art? Like, you know how the welders, like the welding arcs? Like
I'm not
lightning.
sure about that. Plasma, basically, from definition, from my understanding, is conductive gas. Around the atom, it lost electron. Okay, it lost some electron, so it become charged. So you know, it's not non-conductive anymore. It looks like gas, but it's conductive. That's why you can make it TV. You know, you put the electricity in there, it shows different colors. Okay, and that's some of the fancy neon lights they also use the plasma to make. Okay, it's conductive. Okay, usually gas is non-conductive. I think, I'm not the physicist, but I think the some of the electron left the atom. Okay, make it electrical charged. Okay, it's not balanced, the electrical charge inside, so it become conductive. Okay, so that's because of heat. You heat it up, then electrical, some of the electron leaves the atom, so it become plasma. Okay, so it still behave like a fluid motion in terms of motion. Okay, it also experience like fluid-like motion. So in that sense, it looks similar to gas. Okay, in this class, we're gonna cover liquid and the gas, right? Okay, although the plasma look differently electrically, but for the motion, it looks similar to gas. Okay. Any other matters, states of matters? There's actually one more.
Dark matter.
What matter? Oh, dark matter is
Dark
not.
matter.
It's out of scope of this. It's not classified as matter.
Doesn't that technically stand for antimatter?
Yeah, it's not. It's not nothing. It's not my question here.
I don't think they know what it is.
States of matter. Okay, dark matter, antimatter. It's not matter.
Would it be absolute zero?
Yes. Yeah, that's the name of it. You're right. Who answered that question?
Michael.
Oh, Michael. Yeah, good. It's absolute zero. It's absolute zero is the temperature, right? That's a matter when it's a material that reach to absolute zero. If a particle reach to absolute zero, then it become BE. Bose-Einstein condensate. Okay, have you ever heard about this name? when a particle become very, very cold, they lose the status of itself, okay? They become a new state, okay? They're called Bose-Einstein condensate. It's very weird, okay? Actually, this is kind of important now. Do you know they're making quantum computers? The quantum computer, quantum CPU is the Bose-Einstein condensate. You have to keep it cold, near, very, very close to absolute zero. Okay, then the particle actually, just like you go everywhere. Everywhere you can feel this particle. At the same time, it can go different locations, different places. It can work at different things. Okay, that's what the basics of quantum computer. A CPU can, at the same time, can do 10 jobs, you know, different things altogether, because it being observed everywhere. Quantum mechanics, right? So it's very weird. So that's the fifth matter.
Isn't that extremely hard to reach?
It's because you have to keep it extremely cold. It's very difficult. But we did. Human produced the Bose-Einstein condensate in 1991 in University of Colorado, and the MIT, the group actually won the Nobel Prize. See, that's the only Bose-Einstein condensate in the entire universe. Okay, they're never been found anywhere else. Okay.
What's that last word called?
Condensate.
Condensate?
Condensate.
Okay, thank you.
No problem. Okay, just remember, this is the new status of matter. It's not new, you know. Bose and Einstein, actually Bose is the guy actually have the idea of this weird fancy stuff. Nobody believed him. And then he sent his manuscript to Einstein. Einstein looked at it. Hey, that's a good idea. Put my name on it. Then everybody believed since they put Einstein's name on it. So, but that's 1905. Okay. And until 1991, actually, we actually created and proved the existence of that. Okay. It's never been observed in universe, because it's never.
You're saying they reached absolute zero?
Yeah, they reached very, 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 very close to absolute zero. Then this matter changed the status. It changed the behavior. Okay, so.
Isn't there a theory that inside of a black hole gets close to absolute zero or close to this Bose-Einstein condensate?
Like close, but we don't know what really happens inside.
There are a lot of theories about what happens inside a black hole that none can be proven.
Until you put a probe or whatever inside the black hole, then you. But this thing is actually created in the lab. Okay, they made it in the lab. So that's quite an achievement of human being to me, because it's never been found anywhere else in the entire universe. Okay. Hey, the quantum computer is coming, right? You know that there are actually existing quantum computers. IBM has the Q lab. It's free. You can actually play with it. You can apply a count, and they have quantum computer. They allocate about 8 qubits. They call it quantum bits. Then you can use it. If you know how to write a program on the assembly language they use, then you can actually ask the quantum computer to do something. It's free. Google also has some quantum computer also. Okay, so introduction. That's about it, about the introduction. Any questions so far?
So in this class, we're only covering liquid and gas. Can't solid particles move fluidly? So we're not going to cover that if they're small enough, like in silos or whatever.
If it's small enough, I think we okay. This is actually absolutely a good question. Okay, you know what? When I was in PhD, in my lab, I have a group mate. His research is to use solid mechanics to study the motion of the solid particles to represent the motion of the fluid. Okay, we're using different ways to study fluid mechanics. Just like in this class, I'm going to tell you how to do it. But they are indeed, it directly way to study. So for example, in the airflow, there's 3 trillion particles in 1 second going through you. Okay, in the reality, it is the motion of these 3 trillion particles interact to each other, causing the effect you feel. Okay, the reason we don't do that is we cannot study by directly look at the particle is too many. Okay, too many, and you have too many interactions, too complicated. There's no way, before the presence of supercomputer, there's no way a human can actually study and buy that. Okay, using the direct method. You know what I'm talking about, right? Directly, you can actually, theoretically, you can. If you have superpower, then you can calculate the motion of each individual particles. Okay, but because that's one way to study fluid mechanics, but it's not the way we study fluid mechanics here, because you're not using supercomputer to do some simulation here in this class. Okay, we use theoretically paper and a pencil. So we use another way called Eulerian description. Okay, use solid particle is like a Lagrangian description. Okay, so it's different way to study fluid mechanics, but we are not using that way. Okay, but to extend to your question, to answer your question, actually there's one application for particle laden flow. You know, on the flow, there's the particle inside the flow, and the motion of particle we can also study it. Okay, that's also a Lagrangian, you know, procedure. So in that sense, we have to learn the flow first, then to study the interaction between the particle and the background flow. Okay, that's also out of the scope of this class. It's too complicated for this class. In this class, we are studying the background flow only. Okay, not the particle inside the flow. Did I answer your question, Joshua? Okay, but there exists a very, very fancy new way to study fluid mechanics. You forget about everything you're in the last 200 years about classic fluid mechanics. Forget about it. We just directly study the 3 trillion particles interact to each other. It's only possible with a very, very fast computer. For example, like the quantum computer. Okay, if the quantum computer become more applicable, then all the science and technology will change. Okay, a lot of things will change. Okay. Okay, I think that's chapter 1. I want to come on. Okay, chapter 1 also talk about the significant event in the history of fluid mechanics. Can you think of any significant invention or event in the human history related to the fluid mechanics?
In recent history or just history in general?
Doesn't matter, in human history, I think. Which one do you feel it's most significant invention that related to fluids?
Bottled water.
Oh, come on.
Ships,
Plumbing
perhaps?
is important. Plumbing is very important. Thousands of years human history, you have to have a plumbing system, right? Otherwise, this is not called civilization, right? So it comes with the human, society. That's very significant. That's good. One example. Any other inventions?
Bulldozers.
Bulldozers.
The hydraulics.
Turbines.
Turbines, right? Turbines, you can produce energy from the wind, from water, and that's a good thing. Yeah, related to fluid mechanics. Good.
I would say also probably the water wheel is probably the earliest invention to deal with fluid mechanics.
Water wheel. What do you mean by water wheel? You take water.
Like a mill, so like using water to power.
Mill. Okay.
Yeah.
Yeah. Sure. I think those. At least we have probably 4,000 or 5,000 years history of using the water power, hydropower. Great Egyptians, right? Without the hydropower, then not possible for the pyramids. Okay, yeah, that's good. That's some good, inventions. And to me, the most significant one is the Wright brother. I don't know. You don't have to agree with me. Wright brother. 1903. What did the Wright brother do?
Heavier than air flight.
Heavier than air flight. Okay. 1903. We actually leave the Earth's ground for like 20 feet. Okay. And sustained in there for, I don't know how long, half minutes or 1903, December 17th. This is a giant step. From my perspective, in my opinion, it's a huge step. Okay. And we leave the Earth. And about 65 years later, we landed on the moon, right? That's 65 years. It's a blink comparing to the entire human history. We start from leave the ground to the another, you know, it's not planet, but at least to the moon, going to the space, right? It's very, very significant to me. That's totally fluid mechanics. You know, airplane is very, very smart. You know, it's like the reason you can fly is the wing, right? It's just the shape of a wing, a shape of a object that creates the upward force. Very, very smart design. Okay, utilize this very simple aerodynamics, and hey, we leave the ground, then we can fly. Okay, now commercial flight is everywhere, right? So, and I guess soon you will have space travel, right? Elon Musk, you know, he's doing the space tourism also. Yeah, maybe we can go to the space in our lifetime.
That's what Elon Musk's dream is.
Hey, that's a Virgin Galaxy, that's a company. Okay, they're actually working on those space, you know, at least Elon Musk's space shuttle a space capsule, spaceship can be easily, you know, how to say, can be commercialized easily. And, you know, it's very easy for regular people to get on there to fly into the space. Okay, so that's a good invention. I always expect to see in my lifetime like regular people going to the space. Okay, so hey, that all starts from the 1903 Wright brother. Okay, I guess that's it for chapter 1, introduction. I hope I gave you a good introduction on what is fluid mechanics and what the difference between fluid mechanics and solid mechanics, and what is the perspective of fluid mechanics, and how do we study it. Okay. Oh yeah, how do we study it? I forgot to do that. How do we study it? How do we study fluid mechanics? There are 3 methods. Okay. Analytically. Okay, analytically. Oh, sure. Paper and a pencil. Okay, if you can solve the problem, you know the starting point. We have the governing equations for flow. Newton's second law, differential form. Okay, so that's basically the fundamental governing equation for all fluid mechanics problem. Conservation, mass, momentum, energy. We have the equations. Okay, so the first attempt always try to solve those equations. If you can solve it, that's it. That's why we need a mathematician, right? We can solve it, we solve the problem. Any problem we can solve, that would be great. But unfortunately, not like solid mechanics. Fluid mechanics problem cannot be solved. You have the equation, but non-solvable. Okay, the equation name is called Navier-Stokes equation. We will talk about it later. It's a 3D unsteady state partial differential equation, non-linear, non-homogeneous. So basically, it's unsolvable. Unsolvable. I think there's a $1 million award for solving any of the 7 equations. I forget what are exactly those equations, but the Navier-Stokes, the flow equation is one of them. Okay, so if you can solve it, you can try to claim that $1 million. But let me tell you, probably the chance is slim. Okay, it's non-solvable with a certain mass, fundamental of the mass. Okay, so But how do we do it? Then we still have this class, fluid mechanics, right? If unsolvable, so what we spend with our time here? Okay, but that's a strategy. We're engineers, you know. We don't, sometimes we want a solution better than no solution. Even the solution is not that accurate. Okay, we have to, right? We have to have some solution and to make products. Okay, that's what engineers do. So if the original equation is non-solvable, but let's make assumptions. Let's make a problem less general, okay? More easy, more simple. Let's do assumptions. For example, you can assume, hey, it's steady state. Although the flow is not, hey, unsteady, I cannot solve. It's too many independent variables. So the t there, the time there. Okay, let's at least get rid of something. Makes the equation simpler. Okay, that's the what engineers do, right? Always make some assumptions. If the assumption is reasonable, it's okay. So we can make certain assumptions, make the equation look easier, and it become, ordinary differential equation, for example. Then we can solve. Okay, so that's the approach. So in this class, we are now really trying to solve those differential equations in this class. Instead, we are just trying to use the solutions of those differential equations to solve practical problems. Okay, we apply those solutions for the practical problems. So those solutions is from basically solved from heavy assumptions, very heavy, so many assumptions leading to the solutions. Okay, so we apply those solutions to particular problems, and for our engineering purposes. But keep in mind, the solution is under heavy assumptions, may not be very accurate. Okay, keep in mind this. As an engineer, fluids engineer, you need to not only provide the answer, but also control the error. At least know what the error could be. The uncertainty in this world, they call it. You have to know the uncertainties, okay, or errors of your solution to the practical problem. Okay, so that's the first way, analytically. So in this class, we're going to do this. Use analytical solution to apply it to solve some practical problem. So you need to know when you see a physical problem, which equation to use to solve it. That's the critical, right? Problem solving. I feel many of our students lack of this ability. Okay, pick the correct equation for that particular problem. Okay, we will practice it in this class. Very, very important. That's the key. That's the fundamental of the problem solving. Okay. Okay, so if the problem cannot be solved analytically, possible. Okay, some problem you apply those analytical solutions, it's really not good. Okay, you have more than 80% error, so why bother to do that? So if you don't have an analytical solution for a certain problem, then the next choice is doing experiment. You have to rely on experiment, okay? Because you don't have a solution without the experiment then, okay? Experiment has many problems, okay? It's the first one is very expensive, okay? You do an experiment and you have to control the error, you have to do it right, everything. You have to have the equipment or something. Sometimes it's easy to measure something, sometimes it's difficult, okay? Very expensive, okay? I give you an example of very expensive experiment, okay? So, wind tunnels, right? I'm talking about wind tunnels. So in the airplane design industry, you have to rely on the wind tunnel tests, okay, for the designing of the airplane. So why wind tunnel? You realize the wind tunnel. You look at the wind tunnel from NASA. It's so big, huge. You have to place the airplanes in there. So why not just like a toy wind tunnel? We can put a model toy airplanes in there. We can still do the test, right? The problem is small scale test does not reflect the reality, does not representing the real situation. Okay, for experiment, you have to test for the real scale, the real size. Okay, why is that? Okay, I'll give you another example. You know, paper airplane. Can you fold paper airplane? Paper airplane, did you make some before? Or make some with your kids or whatever? I can make a nice airplane, paper airplane. It can slide, it can fly pretty nicely. Right? I guess everybody can do that, right? Okay. So, but if you, the paper airplane, if you make it 100 times bigger, exactly the same shape as the paper airplane, but 100 times bigger, I guarantee you it won't fly. Okay. Vice versa. A 747 fly nicely. In the airport, you can buy those small scale toys of 747. Okay, very small for the kids, right? Then if you throw it, it doesn't fly, it just drops. That's exactly the same shape. Where are the aerodynamics? It tells you with different size, although the same shape is the same, the aerodynamics is different. It works on the large size, it doesn't work on the small size. It work on the paper airplane, it creates enough lift, but it doesn't work on the bigger size airplane, like same size, same shape as the paper airplane. Okay, so in that sense, in experiments, small scale experiment mean nothing. It's garbage. Okay, useless. Because the result, whatever you measured from the small scale experiment, doesn't tell you anything about the large scale situation. Okay, so you see, airplane fly nicely, aerodynamically. I'm sorry, paper airplane fly nicer, aerodynamically sound, but make it bigger, aerodynamic doesn't aerodynamic. It doesn't become aerodynamic sound anymore. Okay, so that's why the real test, if meaningful test is very expensive, meaningful experiment in a lot of application are very, very expensive. You have to make a wind tunnel as bigger than the airplane. Okay, how the heck can you do that? It's really, really difficult. Okay, or you have to do something else, to make it happen. So then it's very expensive. For example, they can make the same Reynolds number with this. They try to still use a small scale tests, but to comparable to some dimensionless number to ensure the similitude. Okay, so a lot of things to do to make the experiment meaningful. So very, very expensive.
Not to mention all the risks that come with trying to simulate airplane flight.
Yeah, of course.
Yeah, what's the third one?
The third one will be, so the first two, but if it doesn't work, then numerically. They call computational fluid dynamics, use computer. They also call it the CFD. I feel this is the future. It's not future, it's a current, basically. People using this. But that's the only way. You can solve all the problems, use CFD, use computer. If you have high performance computer, you can actually, they're trying to solve, numerically, try to solve the governing equation, fundamental equations. It's unsolvable, right? So what's the strategy? You approximate the equation into linear algebraic equation sets, so-called matrix. Okay, linear equation, you have 322, right? Do you? Math 322, right? Linear algebra.
Yes.
That's the fundamental of the science, okay, right now, in the future. Very, very important. Everything, all the differential equation can be break down into, approximate into linear algebraic equations, okay? And then you try to use the computer to solve the linear algebraic equation sets, the matrix. So everything can be solved in a matrix, okay? That's like, I think the old time movie, 90s, they call Matrix movie, very famous. The world is a matrix, that's true. Everything can be solved. And then, but the matrix is not the real, it's not exactly the same equation. It's the approximation. Remember this. That's what engineer likes to do. We like to approximate it. It's not the same equation. We assume it's the same. Then we know the error, the truncation error between the matrix and the initial equation. As long as we can control the error, we're fine. Okay, we will have some solutions. So that's so-called CFD, computational fluid dynamics. We have in ME, mechanical engineering, we have a class 330, ME and 330. We will talk about this in more detail. Okay, experimentally, we have the fluids lab. We will talk about that in more detail, right? So this class 311, we do analytical. Okay, so that's this 3 different methods. We put them all into our mechanical engineering curriculums. Okay. Chemical, probably you have your own lab, fluids lab, right? I don't think you have the CFD part, but at least you have this 311 and the chemical lab you're associated with the fluid mechanics. Okay. So that's truly it for chapter 1, the introduction, I guess. Yeah, I covered everything. Okay, I have 2 minutes. I can entertain maybe 1 or 2 questions. Anybody have?
So with uniform versus the uniform and non-uniform versus steady and unsteady, uniform is when you might have or non-uniform is different
Yeah, just look
velocities.
at the screen here. Look at your screen. The first one, the top,
Yeah.
it's a non-uniform. The second one is uniform.
So I guess I'm more confused with non-steady versus non-uniform.
Unsteady.
Non-steady is
don't confuse. If you don't even think about the uniform or not, when you think about steady or unsteady, steady and unsteady is the time. For example, it's just, hey, pick a location. Let's say it changes with time. For example, just this, let's say this uniform flow. Okay, you are the controller of the wind tunnel. Okay, you set the speed at now 100 meters per second. Okay, now you want to control, you want to change it. I want to change it to 85 meters per second. So what you do? You put in the computer 85 meters per second. Usually the wind tunnel can be controlled by a computer, right? Okay, then the wind tunnel run on 85 meters per second. So the 85 meters per second still look like this. The value decreased, but the flow everywhere is still the same, 85 meters per second. Okay, you're looking at that space, the test section of the wind tunnel. In that test section, the flow is the same everywhere. That become a uniform flow, but it's unsteady. Hey, you change it from 100 meters to 80 meters. Did I answer your question?
So it can be unsteady and uniform?
It can be any combination. This is an example of unsteady and uniform. It can be unsteady and non-uniform, like the test 1 here. You also change the incoming speed from 100 meters per second to 85 meters per second. Then it becomes unsteady. It's ununiform. Okay, use those examples to try to understand what are the concepts. Okay, does that make sense?
Yeah.
So in that example, when you're going from 100 to 85, during that time, it would be unsteady. It's steady at 100, and when it gets to 85, it's steady again, but in between, it's unsteady.
Yeah, you can see that again, because when you talk about time, you will have a range. You're not talking about infinitely, time period. In a certain time period, you are interested, right? It depends on you. You're right. You're absolutely right. When in the transition, that part is unsteady. Then after you change to the 85 meters per second, you never touch it again. Then it becomes steady again, right? It depends on the target time range you are interested. Is that right? Did I answer your question? So you decide, okay? You decide based on the application, basically.
Dr. Zhang, I have a question.
Yeah. Sure.
It's about uniform and non-uniform.
Yeah.
I know that visually it's pretty easy for the X and Y's to actually understand like how that works, but will the third dimension Z ever be a big issue as far as like uniform and non-uniform? It's just the third dimension is typically harder to visualize.
It's the same thing, but you change an angle. If in the experiment you go to the front view, then it becomes third dimension. So you can still see it. You can take picture from other angles, but treat them the samely. But mathematically, later we will talk about just a function. Velocity is a function of x, y, z.
Right.
See if the function, if you can write down the mathematical formula, you will see if it's uniform or non-uniform.
Okay.
Yeah. Good. Okay, I have to let you go. It's 10:48, so it's 3 minutes past. Okay. So see you Thursday. Okay. Is it so far so good, everybody? Yeah, I try to make it understandable. Okay, good. See you Thursday. No homework right now.
Yes, sir.
Okay.